Hi everyone, and welcome to the video on section 9.1 where we look at sequences. The objectives for this particular video are number 1, to list the terms of a sequence. Number 2, determine if a sequence converges or diverges. Number 3, write a formula for the nth term of a sequence. And number 4, use properties of monotonic sequences and bounded sequences. The first thing we want to do is define what a sequence is. And this is a review from what we did in pre-calc when we looked at sequences and series there as well. But what you have in this case is a sequence is defined as a function whose domain is the positive integers. Now, often when we represent a sequence, it's going to use subscript notation. So when n is 1, we'll get a sub 1. When n is 2, we get a sub 2. When n is 3, we get a sub 3, and so forth. The values a sub 1, a sub 2, and a sub 3 are the terms of the sequence. A sub n is what's called that nth term of the sequence, and that just tells you how to get to any term that you want. And then when we see a sub n inside the set braces like that, that represents the entire sequence. Now, one of the things you're going to be asked to do is you're going to be asked to list the terms of a sequence. And when you're working on that, there's two different ways that we can define a sequence. We can give you that nth term, which is what we see here, and a sub n is 3n over n plus 4. Or we could have what we dealt with before also, which was a recursive definition, which we give you one or more terms of the sequence. And then this part, this rule here, where I have, in this case, a sub k plus 1 is 1/3 a sub k squared. What we're doing there is we are able to go, and this tells us how to build the sequence from the previous terms. So let's take a look at the first one here. A sub n is 3n over n plus 4. So I want to list off the terms of a sequence. So I'd have to go through. I'm going to find a sub 1. A sub 1 means I put 1 in for n. So I get 3 times 1 over 1 plus 4. So I get 3/5. I want to find a sub 2. I'll have 3 times 2 over 2 plus 4, which in that case is going to give me 6 over 6, which is 1. And I can just do that for further. So a sub 3 is going to be 3 times 3 over 3 plus 4, which gives me 9 over 7. A sub 4 is going to be 3 times 4 over 4 plus 4, which is going to give me 12 over 8, which reduces to 3 over 2. And I can continue listing off more terms of the sequence just by putting in bigger values, bigger integer values in for n. Now, with the recursive definition, what's going to happen with that recursive definition is I am going to go through, they tell me what that first term is. In this case, a sub 1 is 6. And this rule tells me how to get to the next term. So I know that a sub 2 is going to be 1/3 of a sub 1 squared, which is going to be 1/3 times 6 squared. Well, 6 squared is 36. 1/3 of that is going to be 12. And then a sub 3 then is going to be 1/3 a sub 2 squared, which in this case is 1/3 times 12 squared. And 12 squared is 144. And if I go through, and 1/3 of 144 is going to be 48. And I can continue building that. So I know that a sub 4 is going to be 1/3 times 48 squared, which that will equal 1/3 times 2304. And then when I divide that, go multiply that by 1/3 or divide by 3, I'm going to get 768. So that would be the next term. And I could continue building that. Now remember, when we talked about these two ways of defining a sequence last year, we talked about how the issue you have with the recursive definition, often it's a fairly easy one to work with, but the issue you have is that you always have to go through. If I want to have the 10th term, I've got to know all the previous terms. Where in the a sub n definition here, let's say I wanted to find a sub 10. Well, a sub 10 is just going to be 3 times 10 over 10 plus 4. So I get 30 over 14, which I can reduce that. That would come out to be 15 over 7. So it gives you a much easier way to go and generate a specific term because I don't need to know all the terms before it. Now, one of the things that we're going to be looking at, and it's going to come into play throughout this chapter, is the idea of the limit of a sequence. Okay, and the key idea here, is that a sequence is a function, and so that what you have is that the sequence a sub n will agree with some function f of x when x is an element of the integers. That's z. That z represents the integers. So when x is an element of the integers, these things, the sequence and the function would actually agree. So what we have here is this. Now that's the key idea. Now we're going to let L be a number such that and we're going to let f be a function of a real variable, i.e. a function of x, such that the limit as x approaches infinity of f of x equals L. Okay. Now what this part right here is saying, if that sequence of a sub n is a sequence such that f of n equals a sub n, in other words, a sub n and f of x agree when we're looking at integer values for x. For every positive integer n, then the limit as n approaches infinity of a sub n is also equal to L. So what's going to happen here? They're going to ask you to go, in a nutshell, we're going to ask you to find the limit of a sequence. The limit of the sequence is the limit as x approaches infinity or as n approaches infinity of that general term, of the nth term. Let's take a look at some examples. Okay. Now, in the first example, sometimes it helps to see what's happening on this one. In the first example we have, in this case, a sub n is 3 plus negative 1 to the n. So when I look at that, on that problem, a sub 1 is going to be, when I put 1 in for n, that's going to be 3 plus negative 1. That's going to be 2. A sub 2 is going to be 3 plus negative 1 squared. Negative 1 squared is a positive 1, so that's going to give me 3 plus 1, which is 4. A sub 3 is going to be 3 minus 1, so I get 2. A sub 4 is equal to 4, and so forth. This is just going to continually go between 2 and 4. That's what's going to happen with this particular sequence. So in this case, the limit on this one, as n approaches infinity of a sub n, that does not exist because we're not going towards one particular value. We're oscillating between two. Let's take a look at the second one down here, where we're looking at a sub n is n minus 2 factorial over n factorial. Now, what we want to do on this one is we want to recall simplifying this. You're going to want to simplify that in terms of finding that limit. So this is going to equal, we want to find the limit of that. So I'm going to be looking at the limit as n approaches infinity of n minus 2 factorial over n factorial. Now, you might remember when we talked about these before that you want to go and reduce these. And I know that the smaller one is going to be a factor of the larger one. So in this case, n is bigger than n minus 2. So I know this is going to equal the limit as n approaches infinity of n minus 2 factorial over n times n minus 1 times n minus 2 factorial. In which case, these drop off. And so that will equal the limit as n approaches infinity of 1 over n times n minus 1, which that's going to end up being 1 over infinity, and that's going to end up equaling 0. Let's look at the next one. A sub n is equal to 8 plus 5 over n. So in this case, the limit as n approaches infinity of 8 plus 5 over n is going to be the limit as n approaches infinity of 8 plus the limit as n approaches infinity of 5 over n. In which case, in that particular one, the limit as n approaches infinity of 8, we already know that's 8 plus the limit as n approaches infinity of 5 over n, as basically it's just a constant divided by n, and as n gets very, very large, we know that's going to 0, so that's going to be 8 plus 0, which equals 8. Next one. And this one is an interesting one. Because what we're going to do is we're going to take the limit as n approaches infinity of n times the sine of 1 over n, which as n goes to infinity, we know 1 over n is going to 0, and we know sine of 0 is 0, which means that this is going to be infinity times 0, which again happens to be an indeterminate form. And so what's going to happen here, this is going to equal the limit as n approaches infinity of sine 1 over n all over 1 over n. And now in that case, that's going to be 0 over 0, so I can now apply L'Hopital's rule. The derivative of sine of 1 over n is going to be the cosine of 1 over n times the derivative of that inside function, which is going to be negative 1 over n squared, all over the derivative of the bottom, which is also negative 1 over n squared. And so in that situation there, these drop off. And this is now equal to the limit as n approaches infinity of the cosine of 1 over n. Cosine of 1 over n. 1 over n, as n goes to infinity, that's going to go out, that's going to approach the cosine of 0, which is equal to 1. So the limit of this sequence here is equal to 1. Take a look at what I've done on each one of these problems. Make sure you're comfortable with it, and when you are, move on to the next slide. Another thing that's going to be key when you're working on these things is going to be identifying what is a sub n. So you can go through, and because a lot of determining whether or not the series converges or the sequence converges or diverges depends on working with finding that limit of a sub n. So we have to find it. So a lot of times it's going to be recognizing patterns. Okay, so in this first one that we have there, I have 1 plus, or 1, and then 1/2, then 1/6, then 1 over 24, then 1 over 120, and so forth. Okay. Now, one of the things you might want to keep in mind on this one is that would be, you can think of that as 1 over 1. And you have to look for patterns. So in this case, I would say a sub n is equal to 1 over. And then we have to take a look at the values that we have there. 1, 2, 6, 24, 120, and so forth. What's happening here? That's a pattern of numbers that I hope that you do remember. You dealt with those in pre-calc as well. You'll see this pattern more and more as we progress through sequences and series. But that pattern right there happened to be factorial. That's 1 factorial, 2 factorial. 6 is 3 factorial. 3 times 2 times 1. 4 factorial, and 5 factorial. So when n is 1, I get 1 factorial. When n is 2, I have 2 factorial. So this is going to end up being 1 over n factorial. It's really going to be recognizing that pattern. Let's take a look at this one over here, that particular one. In that situation right there, that 2, I'm going to think of that, put it into the terms of pattern I see there. That's 1 plus 1 over 1, 1 plus 1 over 2, 1 plus 1 over 3, 1 plus 1 over 4, and so forth. So if I take a look at that, I can see a sub n, in this case, is going to be 1 plus 1 over n when I look at that one. The next one I have is what's called an alternating sequence because of the fact that it is alternating between positive and negative. Now, when you see that happening, we know that that's going to involve it's going to involve negative 1 to a power. And really what's going to happen is if you remember back again from pre-calc, when the first term is negative, we know we're dealing with negative 1 to an even power when it's positive. When n is 1, we want to have negative 1 to an even power. And when the first term if the first term is negative, we want to have negative 1 to an odd power. So what happens then is, based on that, we know that when that first term in this case is positive, I'm going to use negative 1 to the n plus 1 power. Okay, and so this is going to be a sub n is going to be negative 1 to the n plus 1 power. That's what will make every even term negative, all over. Now, if you take a look here, this one would be 1 over 1. And then 4, 9, 16, and you'll notice those happen to be squared. So this is when n is 1, I get 1 squared. When n is 2, I get 2 squared. And then when n is 3, I get 3 squared. When n is 4, I get the 4 squared. So this is going to be negative 1 to the n plus 1 over n squared as our general term. And the last one here. In this one, you'll notice that it's more a pattern in terms of how the denominators are being built. It's, when n is 1, I get 2 times 3. When on the second term, I have 3 times 4. On the third term, I get 4 times 5. And in the fourth term, I get 5 times 6, and so forth. So what I have in that case, I can say a sub n is going to be 1 over, but now 2 is 1 plus 1. 3 is 2 plus 1. 4 is 3 plus 1. And 5 is 4 plus 1. So it's going to be n plus 1 times. And then in the next part, 3 is 1 plus 2, 2 plus 2, 3 plus 2, 4 plus 2. So I'm going to get n plus 2. So the general term of this particular sequence comes out to be 1 over n plus 1 times n plus 2. The next thing we're going to be taking a look at is really looking at two different terms associated with types of sequences. And those are monotonic sequences, and then we'll also look at bounded sequences. Because what's going to happen is if a sequence is monotonic and bounded, good things are going to occur for us. Okay, so what we have here, first off, let's define what monotonic means. Monotonic means that the terms of the sequence are either non-decreasing or non-increasing. In other words, if it's non-decreasing, that means that a sub 1 is going to be the smallest term in that sequence. Doesn't mean that a sub 2 can't be equal to it, but a sub 1 will be smaller. And then a sub 2, and we're just going to keep going up. And we know that the next term is always going to be either a little bit bigger than or equal to the previous term. Okay, so the values of the terms are not going down. They're at least staying the same or maybe getting bigger. And when we're looking at non-increasing, then a sub 1 is going to be the biggest term, and that all the terms after it are going to be less than or equal to it. So a sub 1 is bigger than a sub 2. It could be equal. A sub 2 could be equal to a sub 1, but a sub 2 will be either smaller than a sub 1 or equal to it. And that will continue on with every other term. And so one of the things you're going to have to do is identify if a sequence is monotonic or not. And so one of the things you got to take a look at is, again, this sequence here is a familiar one. We know that's 2, 4, 2, 4. In this case, this is not monotonic because I went from 2 to 4. I went up, but to go from A2 to A3, I have to go down. So I'm not moving in the same, I'm not always going up or always going down. So in this case, that one right there, this is not monotonic. The next thing we have here is b sub n, and b sub n is going to be 2n over n plus 1. So I want to look and determine on this one if it's monotonic or not, okay? And really I'm looking at either is this less, is the previous term 2n over n plus 1, is that less than 2n plus 2 over n plus 2 when I go to the next term, or is it greater than? In this case, it will end up being less than. But what I'm going to do is really look at solving this inequality. I can go through, multiply, both sides, get rid of the fraction. So when I cross multiply, I'll get 2n times n plus 2 is less than 2n plus 2 times n plus 1. Now keep in mind, I know that these are all positive values because n is a positive integer. So I don't have to worry about n plus 1 or n plus 2 being negative and changing the sign of the inequality. So I have this. And when I multiply that out, I get 2n squared plus 4n on this one. And when I FOIL that out, I'll get 2n squared plus 4n plus 2. And when I go through and simplify that, subtract the 2n squared and 4n from both sides, I get 0, which is less than 2. Well, that's true. And since that is true, I know that for no matter what value of n I pick, I know the next term is always going to be bigger than the previous term. And so therefore, I know that this sequence happens to be monotonic. The next thing we have is what it means to be bounded. A sequence is bounded above when there is a real number m such that a sub n is less than or equal to m for all values of n. And m is an upper bound of that sequence. Now keep in mind, m, when we talk about these bounds, upper bound and lower bound, we look at these things in terms of a numerical value. And as long as a value is bigger than any of the term of the sequence, then we know it's bounded, okay? It doesn't mean that we have the least upper bound or the greatest lower bound, okay? But as long as we can identify a number for sure that I know every term of the sequence is going to be less than that, I know then it's bounded above. If a sequence is bounded below when there is a real number n such that n, capital N, is less than or equal to a sub n for all values of little n. And that number n is called the lower bound of the sequence. Now, the next part is key. A sequence is bounded when it's bounded above and bounded below. Just because it has an upper bound or a lower bound does not guarantee that the sequence is bounded. It must have both. If it doesn't have both, it's not a bounded sequence. If you're going to tell me a sequence is bounded, then you have to be able to show me that there is an upper bound and a lower bound. Now that we've dealt with monotonic sequences and bounded sequence, let's take a look at the theorem that we're going to be using. Our theorem here states that if a sequence a sub n is bounded and monotonic, then we know that sequence will converge. If a sequence is bounded and monotonic, then it converges. Okay, let's take a look at this. So what I have in this first example, a sub n is 5 minus 2 to the n. So I know a sub 1 is 3. When I put 1 in for n, I get 5 minus 2, which is 3. When I put 2 in for n, I get 5 minus 1, which is 4. When I put 3 in for n, I get 5 minus 2/3, which actually then should be a 1/3 there, not 2/3. And then when I put in 4, I get 5 minus 1/2, which is going to be 4.5, and so forth. But you can see that looking at this, we can see that our terms are increasing in value. And that makes sense because I'm looking at this right here, and I know as n gets bigger and bigger, I know this fraction is getting smaller and smaller. So I'm subtracting a a smaller number from 5 each time. So that right there tells me that yes, I am looking at something that is monotonic. I can make that determination just by looking at this one, that we are monotonic. The next thing I have though is this bounded? And when I look at it in terms of it, whether or not it's bounded, I can look at, we can already know that a sub 1 is 3. So I know that 3 is already a lower bound. So it is bounded below by 3. And then what I take a look at here, as n goes to infinity, as n goes to infinity, this sequence is going to go to 5. So I know that our sequence converges to 5. And so I know that 5 happens to be, in this case, an upper bound of our sequence. So therefore, on this one, that this sequence is bounded and it's monotonic, so therefore I know it converges. Now let's take a look at a second sequence that we have. B sub n is equal to n squared over n plus 1. Now I've listed off some terms for b sub 1, b sub 2, and so forth. Kind of gives us an idea what that this thing appears to be monotonic. We could go through and do the proof of that. We could go through and show that n squared, in terms of that proof, it would be n squared over n plus 1 less than n plus 1 squared over n plus 2. We could go through and do that proof and show that that is monotonic, but the thing that I have on this one that tells me I don't really need to be concerned with that is the fact that if I take the limit on this one. In this case, the limit on there, the limit as n goes to infinity of n squared over n plus 1 is going to come out to be, you can go by L'Hopital's rule, is going to be the limit as n goes to infinity of 2n over 1. Well, that's going to be infinity. So in this case, this sequence is not bounded. So therefore, since it's not bounded, we know that it doesn't converge. And also the fact that that limit does not equal 0 tells me it doesn't converge. The other one that we have is, or it doesn't equal a number. It goes off to infinity. In this case, this next one that we have, c sub n is equal to negative 1 to the n. That alternates. So it's bounded. This one is bounded, but it's not monotonic. So therefore, it doesn't converge. So what you have in these two different ones, this one right here is monotonic, but it's not bounded. So we know it doesn't converge. And this one is bounded because it's going between negative 1 and 1, but it's not monotonic. And therefore, it also doesn't converge. So with that, that does conclude our video covering sequences for this particular chapter. And from this point forward, we will be working with series. So that will make a difference in terms of how we approach these. But some of the ideas behind the sequence will be key in terms of working with series as we go forward. So with that, I want to conclude this video, and if you have any questions, make sure to ask them in class.